Now we're going to look at how we can use Boolean algebra to actually design better circuits. I know, use math to do something useful? To design something? Are you kidding me? Well, no. We left off before with this interesting property of Boolean algebra. That may have led you to ask, gee, are there any other interesting properties? Well, indeed, there are a lot of them, and some of them come straight to us from regular algebra. In regular algebra, we talk about the properties of multiplication, we talk about the properties of addition, and so here we're going to talk about the properties of and the properties of or. And the first are ones that should recall way back to, sixth grade, when we learned about properties of regular algebra. There's an identity, a multiplicative identity, and an additive identity. Well, duh. If you and anything with 1, you get the same thing back. If you OR it with 0, you don't change it. Well, that's what an identity is all about. The commutative property works. A and B is the same as B and A or B is the same as B or A. Duh! Perhaps not quite as obvious, the associative property also works. And, maybe not obvious at all, the distributive property works. You can factor and you can distribute. Now notice I didn't put anything over there in the OR side, which is where we'd usually be talking about foiling. A plus B times B plus C. Turns out that's not quite the same. I know what you're thinking. Why isn't it AA plus BA plus BC plus, which one did I forget? AC. Well, let's see if that's what it comes out to. AA, can't say A squared, plus BA plus AC plus BC. Good enough. Let's apply some of the properties we've seen so far. Okay, well, A and A, that's just A. And then I can factor an A out of BA plus AC. A and 1 is the same as A, looking good. And now I can factor again. I factored an A out of those first two terms. Oh, and 1 plus anything, thing. And A and 1 is A. Ta-da! A or B and A or C is indeed A or B and C. Now in doing that, we pointed out a couple of other interesting properties. A and A is A and not A is 0, if you think about it for half a second. And over on the other side, A plus A, or A or A, is A, and A or not A is always 1. And last, and very interesting, two properties that came from a guy named De Morgan. If you take A and B and negate it, it's the same as negating A and ORing it with B. And the reverse works on the other side. Now, your book doesn't have these algebraic expressions in it, so it's worth pausing the tape right now and writing these down, because you're going to need them for some of the assignments later on. Did you get those? Here's two more for your notes. The first one is the one we started off this podcast with, and the second, I think, is obvious if you look at the first one long enough. All right, what good is this? Well, it's a great way to answer the question, is this an XOR gate? Now, if empiricism is all you want to do, you could build it and try it and see, or you could maybe hand simulate it with ones and zeros. But here's an algebraic approach that's a lot simpler. All right, there's the Boolean algebraic expression that describes that circuit. A or B and AB not. If you're confused by that, pause right here and work it through so you see where that expression came from. All right, using De Morgan's law, I'm going to expand the second term there. And now I'm going to FOIL it. Notice that the first and the last term go away. And I'm left with B and A naught, or A and B naught, which was our definition of XOR. Yes, indeed, Virginia, that's an XOR gate. Now let's see if we can use the same technique for design. Well, I'm stuck for an idea here, and when stuck for an idea, I always turn to OR of ANDs. There's our 4 ones. There's the AND expression in terms of the inputs corresponding to each of those. And now I'm going to OR them all together. So there's our expression for that circuit. Now I could go right ahead and build that circuit. And if I did, it would look something like, this. A lot of wires in there, A's, B's, and C's, nuts going all sorts of different directions. And I've cheated a little bit here because you can see I've used some 3-input AND gates and some 4-input OR gate there at the end. And if I actually had to split those out into 2-input gates, it would about double the number of gates plus a little. So let's simplify instead. From the first 2 terms, I'm going to factor out an A naught. From the last 2 terms, I'm going to factor out an A. Notice that what I then have is B XOR C naught in the first place, from one of those XOR laws, and B XOR C in the second place. And now the biggie. Did you see it? A naught times B XOR C naught plus A times B XOR C is the same as XORing those 2 expressions together and taking the whole naught of the whole thing. That was our other XOR law. So here's my revised circuit. Only 3 gates. And in fact, if I cheated here and used a 3-input XOR gate, it'd only be 2 gates. So, 8 gates to 2 gates through math. And it implements exactly the same truth table we started out with. Sometimes you just gotta love math.